let's move on and look at what what actually are we working with. We have the Earth, this thing that we live on. We live on the surface of this Earth, and we've had to model it in some way. We've got the longitude and latitude, or if you're using the geocentric Cartesian coordinates, we've got this x, y, z. We'll not worry too much about the flat surface, the map that we want to work with in the end just yet. We'll look at the basic models of the Earth as a whole. So we have the Earth, and we have an ellipsoid, a slightly deformed sphere, a ball, like a rugby ball shape, rather than a football shape. That's how we're generally speaking modelling the Earth. It's an oblate spheroid, an ellipsoid. Mathematically simple, which is good because we like that. Unfortunately, the Earth isn't. It resembles this spheroid thing, this oblate spheroid, the ellipsoid, rotational ellipsoid. It resembles it to a good degree, but actually the Earth is more sort of is this potato-shaped thing that we've spoken about. It's lumpy. Both lumpy in terms of the topography that we have, but also lumpy in the general form extended out or as it exists. So that it's lumpy on different scales, but close enough to this ellipsoid form that we can actually use that as a good enough model for calculating our positions. More than good enough, but these things exist. The deformations, the changes, the deviations from this mathematically simple surface exist, and we need to be aware of them because they will influence our measurements. So if we have this dark black line, that's our mathematically simple model of the Earth, this ellipsoid thing. And then this grey line is the actual surface. This is the thing we walk on and we experience, and we go up and down hills into this valley. And we can see that actually it can be above or below the ellipsoid. It's just a matching we're estimating, approximating the actual surface with this mathematically simple thing. So it doesn't follow it perfectly above and below. And then we get to the ocean out here. But there's another thing that we need to be aware of called the geoid. The geoid is an equipotential surface of gravity. Why is this important, and why does it vary? Well, so this surface is telling us what is down. It's a function of how much mass there is beneath our feet, how dense things are beneath our feet, how much the Earth is pulling on us. Now, the centre of gravity is the centre of Earth, but everything pulls on us. Even the cup that you may have on your desk right now is pulling a little bit on you, and you are pulling a little bit on your cup. Insignificant amounts, but everything affects everything else. And the variations in density and mass mean that we have variations in the strength of gravity we experience beneath our feet and beneath our survey equipment when we're measuring. And the geoid defines down, not the surface of the Earth. Whatever we may think of as being down, when we stand on a point here, we may think down is straight down that way, but actually down is, according to the geoid, it's going to be at a right angle to the geoid. So it's slightly off of what you might consider to be down when you're looking up at the stars or looking out over your horizon as you think you see it. It's a technical issue, but it does have an effect. It is not insignificant when it comes to our surveys, when it comes to how we measure. Up and down are perpendicular to the geoid, not to the surface of the Earth or to the surface of the ellipsoid, as we experience them. When we define them in the coordinate system, obviously up and down then become relative to the ellipsoid. So there we have a small problem that needs to be adjusted. Beyond the scope of this course, definitely beyond the scope of this lecture, but for those of you who are reading surveying, you will encounter this in more detail. So if we've defined our surface of the Earth, we've got this potato form, and we want to put a mathematically simple model of the Earth, fit it in there. So nowadays, what we're generally speaking are using is WGS84 or GRS80, which is essentially the same thing, some small shifts due to tectonics and what have you. But the model of the Earth, the size of it, how big is the Earth, is this WGS84 thing. And this is based on the orbit of satellites around the Earth. We've been monitoring satellites since the beginning of the era of satellites, and we've been tracing their course around the Earth, and especially with the GPS satellites and other GNSS satellites, we're tracing their path around the Earth, and that informs us of the size of the Earth and where its center is. And so we can create this model of it. Previously, we didn't have access to this data, but rather we would stand on the surface of the Earth and try and measure its curvature and base our models on that. We know that the Earth has a such and such a curvature, so therefore it must be this big. And that would provide us with a different model. In Sweden and in many other countries around the world, the model used was something called Bessel's 1841, so derived by Bessel in 1841. Made this model of the Earth, and it was quite successful. It's used, as I said, in Sweden and Switzerland, in parts of South America. It was at least used in these places. As I said, it's been supplanted now by WGS84 based models, but it used to be in existence, and we're going to talk about it now just because this data will arise. You will encounter it at some point. You have data that's based in the RT90 system, and RT90 is a coordinate system whereby you take Bessel's 1841 model of the Earth, this sort of orange ellipsoid, and you move it so that it suits Sweden, so its surface matches as best as it can the surface that you're interested in this case Sweden. Which means that its center may not be the same center as the true center of the Earth. But that's not relevant because you're only working up here. This is the only bit that you're interested in. It's a model of the Earth, but it's only locally relevant up here. So this Bessel's 1841, you shift over so that it matches Sweden, and then you can call that RT90. So we have two different ways, at least, I mean, there are many ways of describing the Earth, but relevant for Sweden, which is the case we're looking at here. We have the historical RT90 and their predecessor to that as well. Most of them actually using Bessel's 1841, but just slightly different positionings. And nowadays, the current system that's been in use for getting on for 20 years, it should have been 20 years, but not actually, is something we call CRS-99, which is based on this GPS model of the Earth, with some other details added on. But we have this detail, and this shift over here, this we can mathematically model using that other coordinate system that I spoke about earlier, where we had the geocentric Cartesian coordinates. This shift from there to there, that's something we might want to do using that coordinate system because it helps to define this translation especially quite easily. But that's a technical detail not to be worried about in this course. But we are still on a curved surface, and we've spoken now about RT90, and I've taken up this name CRS-99 based on the GPS model of the Earth. But so, as I said, we're still on the curved surface, and we don't want to be on the curved surface. We want a nice flat map. We want to project from the curved surface up to a flat surface. We want to be here on this flat plane, pretending that the world is flat. At least locally, that might be true. So how do we do this? Well, we have to go up from the curved surface, like we have, to our flat surface, and that's not simple. There are many ways of doing it. So if we take a piece of paper and lay it against our globe, our ellipsoid, it can touch perhaps at one point here. That's fine, we can transfer that information directly. But what about these other places where it's not touching? I mean, you could try and fold the paper over, but it's going to get all wrinkled and scrumpled. We'll look at ways of perhaps doing a little bit of that in the next slide, but generally speaking, you're trying to keep the piece of paper flat against and hold it against the Earth, and you could transfer the information. Maybe you could go take a right angle straight down from the piece of paper, and where do you hit the Earth? Take that information and put it on the map. Or you can go the opposite way around and put your right angle here at the surface of the Earth, go out from the center, up, and where you hit the map, you transfer the information from there up to there. Sure, you can do that. Alternatively, you could go from the other side of the globe, opposite to where this point is tangential to the globe, and then straight through that point of information and push that onto the piece of paper. That's another way. Those are ways of doing this projection. Which one's right? None of them are right. None of them are wrong. They're just different ways of doing it. And we have to, in our metadata for this projection, we have to describe what we've done there. This has to be given by whoever created the map or created the coordinate system. This has to be defined in some way so that others understand that this is what has been done. As I said, we can also, if we want to reduce this distance here, if we don't like this is quite a long distance. The longer this distance is, the more deformation we have, the more inaccurate our map is. So maybe we want to reduce that. So what we could try doing is, say, having 2 points of tangential points. How do we do this? We can make this angle here, or we can make a cone. So we can fold the piece of paper into a cone like a hat and put it on the head of the world. And so it touches, that's actually touching at a line going around here, but we're working in 2 dimensions in this illustration, so you're going to have to accept that these 2 points actually represent a line going around the globe. Or we could just, because we're not actually putting a piece of paper on the Earth, this is just a mathematical model, we can put the piece of paper cutting through the Earth, so it touches again at a circle going around the globe, but it means that the maximum length of this deformation is reduced, and we have 2 points or an entire line where there is no deformation. So that's a couple of different ways of doing it. All of these are possible. As I said, not one of them is better than the other. It just depends on what you want to do, on what you want to focus on. What is the purpose of your map? That will determine which method you choose, which methods you choose. So to now sort of illustrate that a little more clearly, this is the cone. This is that hat going on top of the head, and as you can see, it touches all the way around there, so we get more deformation here. But we can also have that cone pushed through the globe as well, so that the circle, so this tip comes closer to the globe, and the edge of the cone sticks out like a skirt at the sides. That could happen. We have the piece of paper just touching at one point. Not very common. We can do that. Or this one we definitely need to think about. This one is going to come back, where we roll up the piece of paper into a tube and stick the ball of the Earth into that tube, or roll the tube around the Earth, however you want to describe it. But we've rolled it up around, and so we're touching along a line going around the Earth, with distortions increasing farther away from that touching line we get. So this model we will come back to definitely. This one is also interesting for us. So these 2 are important. There are, of course, lots of other ways of doing this, many interesting ways, like the Dymaxion, Buckminster-Fuller, a name you should definitely look up, Buckminster-Fuller. He invented lots of things called the Dymaxion. One of the Dymaxions he invented was this map projection. It's quite good in many respects. Everything has got its right shape, except of course the Earth, but all of the land masses have got pretty much their right shape, and they're the right areas as well. It's all just a bit kind of weird. So nice as it is, it tends not to be used terribly much. So it becomes mathematically difficult to do certain operations on that kind of thing. It's not straightforward.